In this video, we're going to talk about something called viscosity. So what exactly is viscosity? Viscosity is the internal friction within the fluid. So a good example to illustrate this is if you think of honey and water. So let's say if we have an inclined plane. If we pour water at the top of the surface, the water is going to quickly slide down the inclined plane. But now let's say if we pour some honey, the honey is going to slowly drip down. So water has a high flow rate relative to honey, whereas honey has a very low flow rate. And the reason why honey has a very low flow rate is because it has a very high viscosity. So this symbol, eta, is the coefficient of viscosity. For water, it's relatively low. I'm just going to write high, but let's put low instead. And so that's the basic idea behind viscosity. It represents the internal friction within a fluid. So how can we quantify it? Here's another example. Let's say if you have a stationary plate. So this plate is fixed in its position, it doesn't move. And above it, you have a moving plate. And in order to move it at constant speed, you need to pull it with a force. And in between the plates, we have a fluid. Now there's going to be a velocity gradient. The fluid next to the stationary plate is not going to be moving at all. But as you go up, the velocity will increase gradually. The distance between the two plates is the length L. The velocity gradient is the ratio between the velocity and the length between the two plates. So to calculate the required force that will keep the upper plate moving at constant speed, here's the formula that you need. So that required force is equal to the coefficient of viscosity, which is the Greek symbol eta, multiplied by the area of the plates, times the velocity divided by the distance between the plates. So as we can see, the required force is proportional to the coefficient of viscosity. So as the viscosity of the fluid increases, it's going to require more force to keep the upper plate moving at constant speed. And if you increase the area, the required force will increase. In order to move the plate at a greater speed, you need to increase the force. So increase in the speed is proportional to the force required. And the force required is proportional to the velocity gradient. However, the force required is inversely related to the distance between the two plates. Notice that L is in the bottom of the equation. So if you increase the distance between the two plates, the required force will decrease. Now let's talk about the relationship between temperature and viscosity. If you increase the temperature of a liquid, the coefficient of viscosity decreases. To illustrate this, let's return back to our inclined plane. And this time, we're going to pour warm honey at the top and also cold honey. If you try this experiment, you'll find that the warm honey will flow down faster along the inclined plane, whereas the cold honey will travel slowly. So the warm honey has a very high flow rate, which I'm going to abbreviate it with FR. The cold honey have a low flow rate. So by increasing the temperature of the liquid, you can decrease the liquid's resistance to flow. You can decrease the coefficient of viscosity, or its internal friction. And so why does that happen? Whenever you increase the temperature, you can cause molecules to move apart from each other. And as they move apart, the cohesive forces that keep them together are now a lot weaker. So all of the intermolecular forces like London dispersion forces, dipole interactions, hydrogen bonds, because the molecules move apart, those interactions are weaker. To illustrate this, imagine if we have two ions, a positively charged ion and a negatively charged ion. We know that these two ions have a force of attraction that pulls them together. But now that electrostatic force of attraction, is it stronger or weaker when the ions are further apart? Now you're still going to have a force of attraction, but that force of attraction is weaker when they're further apart. To illustrate this, think of a bar magnet. If you have two bar magnets, when you put those two bar magnets close together, you can feel the force of attraction between them if you place the north pole of one magnet to the south pole of the other. But as you move the magnets apart, the force of attraction decreases. And so what happens is, whenever you raise the temperature, the molecules move apart. And as they move apart from each other, the force of attraction that keeps them together, it weakens due to the increased distance. So when you heat up honey, the molecules move apart, there's less cohesive forces within honey, and so the internal friction reduces, and that's why honey, the molecules can flow past each other a lot easier at a higher temperature. And so that's why the viscosity of a fluid decreases with increase in temperature. The molecules move apart, allowing them to flow past each other with much more ease. Now let's work on this problem. A force of 1.9 newtons is required to move the upper plate at a constant speed of 0.25 meters per second in the figure shown below. The area of the plates is 0.5 square meters, and they are separated by a distance of 1 centimeter. Calculate the coefficient of viscosity of the fluid between the two plates. So this is the separation distance. So we know that the required force is equal to the coefficient of viscosity times the area times the velocity gradient. So the force in this example is 1.9. Our goal is to solve for eta. The area is 0.5. The velocity is 0.25. And the separation distance, that's 1 centimeter. So we got to convert that to meters by dividing it by 100. So that's 0.01 meters. So 0.25 divided by 0.01 times 0.5. So on the right side, that's 12.5. So what we need to do is take 1.9 and divide it by 12.5. So the coefficient of viscosity is 0.152 pascals times seconds. So that's the unit for the coefficient of viscosity. Now, part B, calculate the velocity gradient. The velocity gradient is simply the velocity divided by the separation distance. So it's 0.25 meters per second divided by 0.01 meters. And so it's going to be 25 1/seconds. And so that's the velocity gradient in this problem. Now let's talk about the units of the coefficient of viscosity. So if we solve for eta, in order to do that, we need to multiply by L. And then we'll have F times L is equal to eta times area times velocity. And then we need to divide both sides by AV. So the coefficient of viscosity is the force times the length divided by the area times the velocity. The force is in newtons, the length is in meters, area is square meters, and velocity is meters per second. So we could cancel meters. So what we have is newtons divided by square meters times 1/seconds. So if we multiply the top and bottom by seconds, these will cancel. And so the units that we have now is newtons times seconds over square meters. Now pressure is force over area. And force is measured in newtons, area is square meters. So 1 Pascal is 1 Newton per square meter. So we can replace newtons per square meter with pascals. And so the unit for the coefficient of viscosity is pascals times seconds. So that's for those of you who want to understand why the units are the way they are.